Welcome back to the study of calculus and its applications. In the previous lectures, we had looked at the various concepts about the derivative of a function and how derivative is applied in analyzing local maxima, local minima. We looked at the various conditions which tell us how to check whether a critical point is a local maxima or local minima. We looked at the continuity test, then we looked at the first derivative test, and then we looked at the second derivative test for analyzing that a point of critical point for a function is a point of local maximum or minima. So, we will start with the last example that we had been looking at in the previous lecture. So, if we look at the example, namely a firm's production Q as a function of labor. So, the production is Q and depends on the labor. The relationship is given by Q is equal to 6 L square minus 0.2 L cube, where L is the number of workers. So, what is one is interested in? Find the number of workers that will maximize production and sketch the graph. Find the size of the workforce that maximizes the average product of labor and calculate the marginal product of labor and the average product of labor at that point. So, we did that first part and we checked that at L equal to 20 is a point of local maxima for the function Q is equal to L square minus 2 L cube. So, we had done that in the previous example, and this is the graph that we got for Q as a function of L. So, at 20 there is a maximum value, right. So, let us go a step further, and then we looked at what is called the average production on the labor. So, the average as a function of L of labor is production divided by L, total production divided by L. Q as a function of L is this divided by L, that comes out to be 6 L square minus 0.2 L square, L 6 L minus 0.2 L square. So, note this is a quadratic, power is 2. So, this is an example of a quadratic function. So, when we maximize this by looking at the derivative and putting it equal to 0, found the critical points and analyze them, we found that L equal to 15 is the point of local maxima for the average product function. So, for this function L equal to 15 is the local maxima point. So, at L equal to 15 we can calculate what is the marginal of production. So, marginal of production is the derivative of the production. So, that is 12 L minus 0.6 L square evaluated at the value L equal to 15, and you simplify it comes out to be 45. And similarly, the average production that we had in the previous slide evaluated at L equal to 15, if you calculate that, that also comes out to be 45. So, that says that at Q equal to 15, which is a point of maxima for the product function as a function of labor, the MPL, the marginal of production as a function of labor at Q 0 is marginal of labor at Q 0. So, this equality is there for this function. Graphically, this can be shown as follows. So, this green graph is the average production, that is 6 L minus 0.2 L square, and this blue violet graph is the marginal of production, that is 12 L minus 0.6 L square, and 6 L square minus 0.2 L cube, that is the production function that is red, that is not completely shown here. And all the graphs are bigger than 0 because the labor is always going to be positive, right, as it at least going to be some labor. If there is no labor, no workers, no production will be there. And these two graphs, namely the marginal of production and average of production, these two intersect at the point A. So, that is the point A where L 0 is 15 and the value is 45. So, So, this is the point where both of them agree. So, and this is the point L 0 is the maximum point of maxima for the average. So, at the average the point where the average production takes maximum value, the marginal production and the average production, they are equal to each other. So, that is what graphically this is saying. Right. So, let us go over a bit further. Let us find the relation between the average product of labor and the marginal product of labor. So, the relation which we just now studied for the particular example, that marginal production of labor is equal to average production of labor is in fact equality which is true in general, not necessarily only for this example. So, let us look at that scenario. So, let us look at a production function. Production as a function of labor is Q is equal to QL. So, production depends on the labor L. So, the average of this production will be Q by L. So, now let us find out, assuming it is differentiable, we can differentiate this function. So, to differentiate this, Q is a function of L, L itself is in the denominator. So, to find the derivative of this, we need to use the quotient rule, and of course, we are assuming L is bigger than 0 here because the labor is bigger than 0. So, what does the quotient rule give? Is the one function divided by the second function. So, second function square, second function as it is derivative of the first function minus the second function into derivative of the first function. So, L square L into dq by dl. So, dq by dl minus q, and derivative of L is 1. So, this is the derivative. So, if we take 1 over L out common, what we get inside is dq by dl minus q by L. So, that gives dq by dl is marginal of production, and right, and dq by L is the average. So, this is MPL divided by L. So, at the point of maximum, we know that when MPL is the marginal product of labor, this is equal to 0. So, when there is a maximum, the necessary condition says L should be equal to L 0. So, in that case, the 0 is equal to this. So, that gives you at L 0 MPL is equal to APL at L 0. So, this gives us a way of computing, asserting that for any product function as a product of labor, if we look at the average production of labor and then maximize it, then the value at the maximum point L 0 is same as the marginal of the production at the point L equal to L 0. So, this is a general formula, and we verified in the previous example. Let us do a similar analysis for the profit function. For total profit function pi is defined as the total revenue minus the total cost. So, if we assuming differentiability, if we assume everything is differentiable, then the marginal of the profit, so that is a derivative of the profit will be equal to derivative of total revenue minus total derivative of the total cost. So, that says the derivative d pi by dq is derivative of TR with respect to Q minus the derivative of total consumption, total costs with respect to Q. So, this is here we are using the derivative formula. The derivative of the sum or difference is the corresponding sum or difference of the derivative. Now, derivative of TR is denoted by MR. So, that is the marginal of revenue, and derivative of total cost is denoted by M of C, that is a marginal of cost. So, and if Q is a point of maximum, let us call this as Q 0, then pi Q 0 is a maximum, then by the necessary condition we know that d pi by dq evaluated at the point Q 0 must be equal to 0. So, that gives us the relation that MR minus MC evaluated at Q0 must be 0. That means, MR at Q0 must be equal to MC at Q0. So, this gives us a relation that the marginal of revenue is always equal to marginal of the cost at the point of local maximum of the function, that is the total revenue. So, marginal of revenue is equal to marginal of the cost at the point of maximum or the minimum. In fact, but here it will be only maximum because the production is there and profit is there. Okay. So, this gives us a consequence. If MR is bigger than MC, see if MR, so this is from this relation, if MR is bigger than MC in some interval, that will mean that d pi by dq is positive. So, the derivative of the profit function is strictly bigger than 0. So, by our result on calculus, that implies that the function must be strictly increasing. So, MR bigger than MC implies profit will be increasing, and similarly, if MR is less than MC, then the derivative is less than 0. So, the theorem on calculus will tell us that if the derivative of a function is strictly less than 0, then the function is decreasing. So, that says that if marginal of revenue is less than the marginal of the cost in some interval. So, this is not at a point now, this is at an interval because we are applying it in a interval. So, if in a where q is varying, if in a interval marginal of revenue at every point in that interval is less than the marginal of the marginal cost at every point, then the profit must be decreasing. So, these are properties about MR and MC in an interval. So, if MR is bigger than MC in an interval where Q is varying, then profit will be increasing, and similarly, if MR is less than MC, then the profit will be decreasing. So, let us now look at another scenario where the demand function for a good is given by P plus Q equal to 30, and the total cost function is given by T of C, that is the total cost function as a function of Q is Q square by 2 plus 6 Q plus 7. So, this relation P plus Q equal to 30 helps us to write P in terms of Q or Q in terms of P as and when we require it to be. So, total cost as a function of Q, the quantity produced is given by this. So, as a consequence of this, we want to find out the level of output that maximizes the total revenue. So, to maximize the total revenue, first we have to calculate what is the total revenue function and then maximize it. So, total cost is given, right, and relation between P and Q is given. So, this will help us to write what is the total revenue and maximizes. And we also want to find out the level of output that maximizes the profit, and then look at calculate MR and MC at these values. So, all this we want to do. So, let us try to solve the first one, try to write the revenue. Okay. So, since the total cost is given by this and P plus Q is equal to 30. So, from here at least we can straight away get that marginal of the cost is differentiate this. So, that is the derivative of T C. So, 2 times Q by 2. So, 2 cancels. So, that is Q, 6 Q gives the derivative 6. So, marginal of revenue is equal to Q plus 6, that comes directly from here by differentiation. Let us calculate the total revenue. The total revenue is the quantities produced and the price. So, P into Q, and the value of P is got from here 30 minus Q. So, when you put this value and multiply, total revenue depends on Q by the relation 30 Q minus Q square. So, we want to maximize this total profit. So, what is the process for maximizing? The calculus says first find out the derivative of this, put the value of the derivative equal to 0 and find out the points where this possibly can happen. So, let us do that. Derivative of TR. So, 30 Q, that gives you 30, and minus Q square gives you minus 2 Q. So, again using the theorem that derivative of the difference is the difference of the derivatives, we find the derivative of the revenue is 30 minus 2 q, and the point where possibly it can have a maximum value is q is equal to 15, because 30 minus 2 q equal to 0 gives you q equal to 15. Can we say that q equal to 15 is the point of maximum? Well, there are two ways of deciding that. One can decide by the first derivative itself. Look at 30 minus 2 q, right. So, on the left of it, that means on the left of the point q equal to 15, 2 q will be less than 15. So, this will be positive. So, derivative is positive on the left. So, the function will be increasing on the left side, and it will be negative. So, it will be decreasing. So, the functions will be going up and then going down on the left to the right. So, q equal to 15 by the first derivative test itself tells us that q equal to 15 is a point of local maximum. We can also apply the second derivative test here, because this function is differentiable. The second derivative exists, and the second derivative for this is equal to minus 2, because 30 will give you derivative 0, minus 2 q will give you the value minus 2. So, the derivative at every point is negative. So, q equal to 15 by the second derivative test must be a point of local maximum. So, let us find out the total profit function for this, because we want to maximize the total profit function. So, the total profit is total revenue minus total cost. Total revenue, just now we have found this, and minus the total cost. So, we put those values and simplify, that comes out to be equal to 24 q minus 3 q square by 2 minus 7. So, to maximize this profit as a function of q, we look at the derivative. So, derivative is 24 minus this 2 comes down, that cancels it, that is 3 q. So, derivative of the profit function with respect to q is 24 minus 3 q. So, the profit will be maximum when 24 implies 24 minus 3 q must be equal to 0. So, if that is the case, that is a necessary condition. So, that gives you q equal to 8. So, when q is equal to 8, there will be maximum profit. But what is the price at q equal to 8? That we have to look at the price and q relation. Okay. But anyway, we can also calculate the marginal of revenue at q equal to 8. So, this is the marginal of revenue that we found as 30 minus 2 q in the previous slide. So, that is at q equal to 8 is 14. And if we calculate the marginal of the cost at q equal to 8, that also we had found out as q plus 6. So, evaluated at 8 is equal to 14. So, marginal of revenue at the point of when the revenue total profit is maximum, that is q equal to 8, is equal to the marginal of the cost at q equal to 8. Now, so this was the profit maximized when q is equal to 8, right. Right. So, if we want to find out the profit at that point, we can use that relation p plus q is equal to. So, let us just go back and see what was the relation between p and q, so that we can find out the maximum for the profit also. So, we had p plus q equal to 30, because maximum happens when q is equal to 8. So, when you take it that side, to p is equal to 22. So, that gives you the maximum profit. So, this is how calculus is applied to the various scenarios in economics, commerce and management problems. Let us now look at what is called the absolute maximum and absolute minimum of a function. So, till now mainly we have been looking at what are called the local maximum and minimum. That means, in a neighborhood of that point, the value is the maximum value is the largest value, or in a neighborhood of that point, the value is the smallest value. We would like to know, given a function in all its domain, we want to know what is the largest value the function can take. So, we want to know what is the largest value the function can take in its domain. So, let us define a point C1 is called a point of absolute maximum for a function. whatever its domain may be. So, if f of C1, the value at the point C1 is bigger than f of x for all x in the domain of the function, whatever be the domain of the function, right. And similarly, and the value f of C1 is called the absolute maxima of the function. So, the point is called the point of absolute maximum, and the value that the function takes, the largest value of the function, is called the absolute maxima of the function. Similarly, we can define what is called the absolute minimum of the function in the domain of the function to be the point C2 is called the point of absolute minimum if f of C2 is less than or equal to f of x for all x in the domain of the function. So, this value f of C2, this value of the function at that point of absolute minimum is called the absolute minima of the function at that point. Right. So, it is quite clear that absolute maxima of the function is the value which is the largest in the domain of the function, and at the point where it takes that value is called the absolute point of absolute maximum, and similarly point of absolute minimum and the absolute minima of the function. So, the problem we want to discuss is, given a function, how do you locate the possible points where the absolute maximum or the minimum can occur, and how to decide what is the absolute maxima and what is the absolute minima of the function. So, for that, let us observe that if a point x is absolute maxima or absolute minima, then it is also a local maxima or minima, right. So, that says that the possible points where which you should be looking at, which you should be analyzing to locate the absolute maxima and minima are the points where local maxima and minima can occur. Collect these points, find out the values of the function at these points and see which is the largest, which is the smallest, right. So, let us look at these values. So, the first are the points in the domain where the function is not differentiable. These are possibly some points where the function is not differentiable, or where the first derivative is equal to 0, the function is differentiable at interior points and the derivative is equal to 0, or the points n points in the domain of the function. Could be some interval and the end points of those intervals are the possible points. So, these are the three set of points which we analyzed, looked at for local maxima minima also. So, those are the same set of points where where possibly the function can have absolute maximum or minimum, because the reason being absolute maximum is also a local maximum. But one has to ensure that this absolute maximum or minimum exists. So, a theorem that we the maxima minima theorem that we stated when we looked at the continuity of the functions in a domain said that if f is a function defined on a closed bounded interval, and if this function is continuous, then it is bounded and attains its maxima and minima. So, that theorem is very useful in ascertaining that a function has a has a absolute maxima or a minima in the domain. So, mostly we will look at the domains which are closed bounded intervals and the functions which are continuous. So, once that is ensured, you look at the points, these set of points where f is differentiable, f is not differentiable, derivative exists and is equal to 0, or the set of points which are end points. Compute the values of the function at these points and compare and see what is the maximum or what is the minimum value of the function. So, we will continue our lecture in this discussion of absolute maxima minima in the next lecture. Thank you.